I saw this integral on YouTube, and this is not a very easy integral. I have my method of doing it. There's some difference, so I want to share with you. Now, first, uh, I use these two in a denominator as partial fractions. It can consider as 1 over x plus 1 over x plus 1. And we can determine the coefficient on the numerator. This is 1, this is minus 1. Okay, that is the partial fractions for the first part. And for the second part, for this one, this is the derivative of arctangent square. This derivative is a true arctangent over x squared plus 1, right? So I just multiply by 1/2 to make them equal. Yeah, good. So then this one has a two parts. The first one is a 1/2 integral from 0 to infinity, and d arctangent square over x. Okay, that is for first part. The second part is 1/2 integral, and this is d arctangent x square over x plus 1. Okay, so and this one is equal to 1/2 is a common factor, is j1 minus j2. Okay, good. This is j1, this is j2, and this is given integral I. So I is equal to 1/2 j1 minus j2. I just consider j1, j2 separately. j1 is this one, is integral d arctangent x square over x. Okay, I am using substitution. I let theta be arctangent x. Then x is equal to tangent theta. So my integral become this will be tangent theta. On top will be d theta square. Yeah, so this is equal. And this will be equal to, or change the boundary, sorry. When x equal to 0, theta is 0. When x equal to infinity, it's half pi. So my integral becomes from 0 to half pi. This will be 2 theta d theta, right? Yeah, written 2 in the front. This will be theta d theta over tangent theta. And that will be 2, 0 to half pi, theta times cotangent, right? Cotangent theta d theta. Yeah, this will be equal to 0 to half pi theta. Cotangent theta d theta is d log sine theta. Yeah. Now then I can use by parts, right? This is equal to 2 u dv becomes u times v from 0 to minus v du. V is this, du is d theta. So it's log sine theta d theta. Okay. For the first part, when theta is half pi, this is 0. Log 1 is 0. It's easy. When this one approaches to 0, this is infinitive. This is 0. So I'm prepare for this will now satisfy the L'Hopital's rule, right? This is infinitive. This is infinitive. So when x approaches 0, this will be taking derivative is a cosine theta over sine theta. And this is the negative theta square. So this is approaching to theta times cosine over sine. And when theta is approaching to 0, this is approaching to 1. This is approaching to 1. This is approaching to 0. So the whole thing approaches to 0. Therefore, this one is approaching to 0. Minus 2. For that, I have a video dealing with this integral. So I'm using the result. I'm not repeating here. If you want to see the detail, just go see the other video. The link is below, so you can easily access to see that video. That is this integral is this. Therefore, my J1 is equal to pi log 2. This is my J1. Now J2. J2 is this. The J2 is this. J2 is integral from 0 to infinitive. This is d arctangent x squared over x plus 1. While I'm using same substitution, let theta be arctangent x. Then x is equal to tangent theta. And then the boundary will be same from 0 to half pi. This will be tangent theta plus 1, right? This will be d theta squared. Okay, so that will be equal to 2 theta. 2 theta d theta, right? Theta d theta. And tangent theta plus 1 is from 0 to half pi. Now, if I multiply by cosine, both top and bottom, this will become, this will be theta cosine theta d theta, and this will be sine theta plus cosine theta, right? For this integral, I have another video showing this result. That is equal to times pi square over 16 plus pi over 8 log 2 minus g over 2. G is a Catalan constant. So, okay, if you want to see the detail, you can see the video, and the link is below. So I'm not repeating the process, but rather use the result. Now then, my I is half j minus j2. So my I is equal to 1/2 j1 minus j2. That means this is this one minus this one times 1/2. So that is end up with pi square over 16 plus 3 pi over 8 log 2 plus half g. G is a Catalan constant. Okay, so that is the result for this integral. Okay, I think it's not a very easy, but it's a fascinating integral, and I hope you can go see my other videos. One's dealing with this one, the other one is dealing with this. So okay, so I get a result, and hope you like it. Thank you for your watching.